領域展開
Hello and welcome back to Dini Teaches. Today we're going to be talking about uniform circular motion. So, what is uniform circular motion? Well, think about something moving in a circle. Let's say this dotted circle is a path, and this little black dot is an object going around that path. Let's also say that this object is moving at a constant speed, which means as it goes around this circular path, its speed is not changing, aka the magnitude of velocity is not changing. And there's actually a lot of examples in your real life that you can think of that follow uniform circular motion. One example is the sun and the earth. The sun acts as the center of the path, and the path itself is the orbit that the earth has around the sun. So this lovely blue marble, as it's called, is orbiting the sun, aka moving in a circular path. Another example from your day-to-day life is a ceiling fan. If you look up and look at a ceiling fan, its blades are all moving in the same direction in a nice circular path. Of course, this drawing is of a certain perspective, so it's not going to look like a circle, but if you are right under a ceiling fan, you'll see the blades are moving in a circle pretty consistently, and by consistently, I mean the speed isn't changing. And that is the key here. In all of these examples I've given, there is a small but important distinction I've made, and that is saying that in uniform circular motion, speed is constant. I said speed, not velocity. These are entirely different concepts. Remember that velocity has magnitude and direction because it's a vector, while speed is just magnitude. Let's quickly sketch something moving in a circle, and hopefully this will become a bit more obvious. Let's say we have an object like this little black bead moving in a circular path, and arbitrarily let's call this T1, T2, and T3, meaning time 1, time 2, time 3, which is essentially I'm just saying that this object is moving in a circle, and at time 1 it's over here, at time 2 it's over here, and at time 3 it's over here. Now, I'm not the best artist in the world, but you can see that the length of these vectors are all relatively the same. And what are these vectors? These vectors are velocity vectors. These velocity vectors all have the same length. And that means that it has the same speed at every time. Time 1, it has the same speed. Time 2, it has the same speed. Time 3, same speed. Because, as you all remember, of course, speed equals the magnitude of velocity. And magnitude of a vector is, of course, length. Let me write that down. Magnitude of velocity vector is its length. Like I said, speed is constant here. I've explained it probably 3 or 4 times already. But velocity is not constant. Remember, velocity has direction. And so if you look at time 1, what direction is it going in? is kind of going up and to the left, you know? A little bit this way, a little bit that way. Now at time 2, it is going less upward and more to the left. And at time 3, it's going down and to the left. Now, I don't know about you, but those sound like 3 entirely different directions to me. And if at 3 different times direction is changing, then that means velocity is changing. AKA, velocity is not constant in uniform circular motion. This is a huge thing that people get wrong on their physics exams and whatnot. They think uniform circular motion, of course, uniform, everything stays the same. Not quite. Velocity does not stay the same. You cannot say that. The magnitude of velocity, or the speed, that stays the same. That's where the word uniform is coming from. It's because of the speed, not the velocity. So drill that into your mind. It's really important. People mess it up all the time. Don't be that. Don't be that guy. Now, I've been saying a lot, oh, velocity's changing, blah, 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 blah. How do we actually quantify this change in velocity? Think back to some earlier concepts. What is change in velocity? Give you a couple seconds to mull it over, and I'll tell you, the change in velocity means acceleration. If you didn't remember that, that's fine. Just go back and review the acceleration video and hopefully you'll get back on track. As I've said, acceleration is the rate of change of velocity. However, this acceleration, this uniform circular motion acceleration, only changes velocity direction, not magnitude. And how do I know that? Well, probably 50th time I've said this in this video, but magnitude of velocity is speed. Really drill that home. So this acceleration is not actually making the object going along this circular path faster, even though the word acceleration might make you think it is. In fact, this acceleration is only affecting the direction of the velocity. It's changing what direction this object is moving over time. And that should intuitively make a little bit of sense. I'm going to scroll up and show you my little path once more. This object, if you think about an object going in a circle, the object needs to change direction to stay going in a circle. If this object didn't change direction, wouldn't it just go in a straight line? So there needs to be an acceleration to shove the velocity direction around in a circle. So we know for a fact we have an acceleration, and the object going around this circular path has a mass. So we have a mass. Looks like we have an M and an A. That is striking some physics bells in my head. It's making them ring really loud. M and A. That sounds important, and that's because it is the two ingredients to Newton's second law, F equals ma. So what does this mean? We have an acceleration on an object going around in a circle. And this object also has a mass, which means there must be a force involved. In order for the object performing uniform circular motion to continue doing uniform circular motion, there needs to be a force that is actually applying the acceleration. Before I answer that, though, I'm going to go over some itty-bitty circular motion concepts, and hopefully they'll make intuitive sense. The first thing I want to mention is the velocity vectors I've drawn in this path. Do you notice anything about them in terms of the path? Well, if you said that they're tangent to the circle at the instant the object is there, you are correct. You'll notice that this object, I'll highlight it in green at time 1, at that instant, if it's going around the circle, its instantaneous velocity is tangent to the circle. Now, what'll happen in the next instant? Obviously, I can't draw the next instant, but I'll draw another object very close, and I'll draw it in red to differentiate it. So it's moved a little bit. This is like the next second of the path. What is the velocity going to look like? Well, it's still going to be tangent to the circle, but now that it's moved, that tangent is different. It's more this direction. And hopefully you can tell by my drawing that this first black vector and this new red vector are not going the same direction, although they are the same length. Hopefully you can use some intuition to figure out why the velocity vectors are tangent to the circular path. The path itself is just what the object is following. And so, in order for the object to continue on the circular path, the direction of its velocity needs to follow the direction of the circular path. And at each tiny microscopic instant of like 1 nanosecond, its velocity is going to be going tangent to the circle, and in the next, let's say, nanosecond, it's still going to be tangent in order to stay on the path of the circle. If you were to zoom in really far into this path, here, I'll even make a little diagram for it. Let's say this is just one chunk of a circular path. Pretend this goes on and is a perfect circle. Obviously, my drawing skills aren't up to par, but let's say we have this object here, and it's again moving around the circle this way. Its velocity is going to be going tangential to the circle. And if you were to zoom in on this little region right here, you'll notice for the instant that the object is at this part of the path, the tangent line, aka the direction of the velocity vector, is pretty much equal to the direction of the path. The red and the black line at the very instant of this object being in that position are indistinguishable, which means having a tangent line velocity vector is allowing the object to continue on the path shown by a circle. And it may not look very obvious, but if you were to zoom in infinitely, a circle will look like a straight line, or at least the little tiny chunk of circle you're looking at, and that straight line is going to be exactly what the tangent line will look like, which means the path and the tangent line are the same. And that is why an object with tangent velocity vectors to a circle will continue going along a circular path. It's a really confusing concept, and I don't blame anyone watching this in being confused. It is something that's kind of hard to wrap your mind around. But with enough practice, and hopefully with some more intuition building over time as you learn more physics, it'll make a little bit more sense. Now, back to acceleration. If you remember, acceleration is equal to the change in velocity over the change in time. So we have, in this example, two vectors. We'll use t1 and t2. Two vectors at different times, and the velocity is changing. So how can we find the change in velocity over the change in time? Well, we can use vector subtraction. Let's brush up on those skills, shall we? Let's do the vector at t2 minus t1. And these are vectors, so I'll add the lines. In fact, I will call them v2 and v1, meaning this is v2 and this is v1. So we have our original v2 and we have v1, and I'm going to move it and reverse the direction. So instead of going up and to the left, it's going to be going down and to the right. We'll use the tip to tail technique, and then we have the subtraction vector being the tail of the first vector to the tip of the new vector, and this red vector I've just created is our delta v vector. If that was confusing, go ahead and watch the vector subtraction video I've made and maybe do some practice on vector addition and subtraction while you're at it. Let's move this vector back to t1, and I want you to look at it and see where it's pointing. Okay, keep that in mind, and let's try t3 minus t2, or let's stick to the naming conventions, v3 minus v2. I'm going to call this delta v1, and I'll call this vector delta v2, just so that my notation is clear. I'll do the same process, taking v2, reversing the direction, bop, bop, tip to tail, right about there is good, and beautiful. Now we have delta v2, gonna move this vector back to t2. Looks like I may have been a little off on the lengths of my vectors, which is fine. The delta v2 vector should kind of look like this. I am definitely not a good artist in terms of math diagrams, but hopefully I'll get better as time goes on. Now, we have two vectors here, delta v2 and delta v1. Is there anything about these two vectors that strike you? If you said that both of those vectors are pointing to the middle of the circular path, you get a cookie or something, because that was a very good observation. So what can this tell us about acceleration during uniform circular motion? Well, this shows us that acceleration during uniform circular motion points to the center of the circular path always. And that's very, 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 very important. You're definitely going to want to remember that uniform circular motion acceleration points towards the center of the path no matter where it is, no matter where your object is. And this acceleration has a specific name. This is called my handwriting. Centripetal acceleration. And it is often written as A sub c. This is a big concept, so definitely remember centripetal acceleration during uniform circular motion always points to the center of the circular path. You should rewind and listen to me say that like 400 times so that it just gets grilled into your head. It's something you really, really got to remember. So this AC, this A sub c centripetal acceleration value, what is it doing during uniform circular motion? Well, remember how I spent a long time talking about the tangent vectors of velocity to the path of a uniform circular motion object? Well, something has to keep those velocity vectors actually tangent to the circle. They don't just change to be tangent by themselves instantaneously. There needs to be a little nudge in the right direction. And that's exactly what centripetal acceleration is all about. So let's go back to our very first diagram about this object here. So you'll notice some very interesting things. Like I said, centripetal acceleration is always going to point towards the middle, so I'm going to do the liberty of drawing some centripetal acceleration vectors for each of these times t1, t2, t3. Now, a couple things you're going to want to keep in mind, and these are all important to a degree. Hopefully you're noticing that the velocity and the acceleration vectors are perpendicular, meaning there's a right angle in between the velocity vectors and the acceleration vectors, and hopefully that makes sense. If you know your way around geometry a little bit, the tangent line to a circle is always going to be perpendicular to the radius vector going to that point. And since the acceleration vector is in the direction to the center of the circle, it's essentially pointing around this radius, or not around, it's essentially pointing in the same direction if I were to just draw the radius to each of these points. It's exactly the same direction, even if my drawings dictate something else. They should be the same. So it would make sense that a tangent line and a radial line would be perpendicular. Now, acceleration is always a hard concept to kind of wrap your head around, so here's how I like to look at it. Acceleration in its direction, if you're looking at it visually, is nudging the velocity in a different direction. So let's look at t1. This original black t1 vector is pointing up and to the left a little bit. And our acceleration vector at that moment is pointing down and to the left. So if you think about it, how should the velocity change based on this acceleration? Well, the acceleration points towards the change in velocity. So if the acceleration is pointing leftward, our velocity should be more left moving forward. And if it's pointing down, our velocity should start turning a little bit more down in the next instant. And you can see that in t2. Comparing the directions of these two vectors, t2 is a lot more in the left direction and a little bit less in the up direction. So that means our acceleration shoved the velocity vector more to the left and a little bit down. Not down enough to actually point down, but down in a way that made the up direction, or the y component of the vector, a little bit smaller. And the same thing happens in between the t2 and t3 velocity vectors. The acceleration vector at t2 is pointing a little bit to the left and a lot a bit down. And the next time we see a velocity vector is at t3, and it's still pointing to the left, but instead of pointing up, it's pointing down, which means our acceleration vector is successful in nudging that velocity in the correct direction to remain in the circular path. So now that I've explained that a little bit, try and predict what the velocity vector would look like right about here, and we'll call it t4. I'll give you a couple seconds to think about it. Well, I think easily enough, we can graph this acceleration vector just because it's nice to look at. And so our acceleration vector from t3, it's pointing to the right and down, which means the next instance we should be able to see a change in velocity being either less into the left direction or it moved all the way into the right direction, and a lot more in the downward direction. So let's draw this supposed velocity vector. It'll probably look a little bit like that. And There's a couple ways I figured that out. The first of which is velocity is going to be tangent to the circle. So in the little instance here of a circle right after the point, I saw what the tangent line would supposedly look like, and I drew it to the best of my ability. The second instance I saw that kind of helped me draw this new velocity vector is to create somewhat of a right angle in between the acceleration and velocity. And I said somewhat of a right angle, not because it's not a right angle, but because I am terrible at drawing, and so the way I drew it is probably not an accurate right angle, but it is supposed to be a 90-degree angle. Absolutely a right angle. And if we look at the velocity at t4, it looks like it's going to the left a little less, as in the x component, let's say, is shorter, and it's also pointing a lot more downward, or the y component is pointing a lot more downward, which is exactly what we predicted from the acceleration vector from t3. Even though I've gone through a lot of explanation here, I know it's going to be confusing. It's really hard to kind of wrap your mind around acceleration, especially when you go into physics thinking acceleration is something different than it really is, because the word in modern life is not used in the way that it's used in physics. So all you need, I think, is some more practice if this is still confusing for you. Going back to centripetal acceleration, I want to explain the word centripetal a little, because it's probably a little likely that either you don't know what it means or you've just never heard the word before. So centripetal, by definition, means moving towards a center or axis. And it's derived from the word centripet, which is Latin for center seeking. And looking at the vectors of centripetal acceleration, you can probably imagine why they named it centripetal, aka center seeking. It's all pointing to the center of this circular path. Perhaps that's a way of helping you remember what centripetal acceleration really is. It's great and all that I've explained centripetal acceleration, but how do we actually calculate such a thing? Well, you can find centripetal acceleration from the speed and radius of the path being taken will lead to a sub c. And this equation is a sub c is equal to the magnitude of velocity, or the speed, squared over r. Now, I'm not going to do a derivation of how I got this acceleration equation right now. I might do one in the future. But for now, just keep this equation in the back of your mind. Now that we have an acceleration equation, I want to do a very quick example. Let's say we have a circular path here and an object here, and it's moving this way around the circle. The mass of the object is 50 kilograms. The magnitude of velocity, or the speed, is 10 meters per second, and the radius of the path is 20 meters. So 20 meters. Now I want you to try and find the value for centripetal acceleration. You can use the equation AC equals magnitude of velocity, or speed, squared over r, and you can find that speed squared is going to be 10 squared, r is 20, so that's 100 over 20, which is 5, and that'll be 5 meters per second squared if you remember your acceleration units. Now, I mentioned some time ago, in order for acceleration on a mass to exist, there needs to be some kind of force involved, as per Newton's second law, F equals ma. So we have an acceleration, and we have a mass. So why don't we try and figure out what this theoretical force's value would be? Our mass is 50 kilograms. Our acceleration is 5 meters per second squared, which gives us 250 newtons. Great, so we know that there's a force of value 250 newtons that is inducing the acceleration that is felt by the object continuing on uniform circular motion. So what on earth is this force? Well, you're in luck, because the name is pretty easy to remember. This is the centripetal force. Exactly the same name as the acceleration we have before. And that's because the centripetal force is found using centripetal acceleration. And you might be thinking, hey, wait a minute, doesn't centripetal mean center seeking? Well, you're right, it does. The force vector is also pointing to the center of the path. And you might remember from our Newton's second law video that force and acceleration point in the same direction, and so it should make sense why force here is also center-seeking if the acceleration is center-seeking. Let's do some quick equation analysis here. We've got two big equations we're working with here. We've got F equals ma, or Newton's second law. We also have centripetal acceleration is equal to speed squared over r. Now, we can combine these two in order to create the equation centripetal force, designated as F sub c, is equal to m speed squared over r. Hopefully you can see how I did this. I just plugged in this AC value for the a in F equals ma and then added the c subscript here. But this is going to be your equation for centripetal force. Now, this centripetal force could be anything. It could be tension. It could also be the normal force. It could be gravity. Centripetal force can be anything. So that's a little different than the other forces you've learned so far, because it doesn't have a real designation in reality. With tension, it's always a rope or a cable or something like that. Normal force is the ground pushing back against objects upon it. Gravity is due to the gravity of any planet you're on, or the gravitational force in between planets or whatnot. But centripetal force can be any one of those three, so it's a little different than the other forces you've learned. And that's why it's called a non-real force. Does that mean centripetal force doesn't exist? No, it doesn't. Centripetal force is real. It's called non-real since you wouldn't call anything just a centripetal force. It's always something else first. So there can be a tension force, and it just so happens to also be centripetal force. There can be the force of gravity, which just so happens to also be centripetal force. There is no such thing as just centripetal force. It always has to be something else first, if that makes sense. Now that we have all this background on centripetal acceleration, centripetal force, and how uniform circular motion generally works, let's do some quick examples. Let's say we have a pendulum here, and I'll show the different possible states it can be in with these dotted lines. Ah, very wonderful drawing by me. Let's say that this ball on the end is 20 kilograms. Let's also say that the string that this pendulum is made out of does not stretch. And it stays at 1 meter long. Let's also say that the string will break if tension force is greater than 100 newtons. And the question I'm asking is, how fast can the pendulum spin before breaking? Now, this looks a little confusing, and rightly so. It's kind of an odd question. So let's work with what we have and try and figure out what we're looking for from there. We have a mass. Mass is 20 kilograms. We also have the radius of the circular path, and that is 1 meter. And keep in mind, this is definitely a circular path. It's a string that doesn't move, which means the radius is always constant. So we can look at the path it's taking, and you can tell just by this constant radius circle I'm drawing, it is definitely a circular path, even if my drawing skills aren't exactly up to par. So we have mass, we have a radius, and we also have a force of 100 newtons. So this force is the tension force. And if we go back to our diagram of the pendulum, which way is this tension force actually applied? Well, it's applied up the string. I'm also considering gravity to not really be a factor in this problem. We'll have more complex problems later, I promise. But because that tension force is moving into the center of the circular path, that means the tension force here is centripetal force. And hey, I seem to remember us discussing a centripetal force equation. So why don't we go ahead and write that down? You know, could be useful, could be useful. Fc is equal to m speed squared over r. You know, I'm looking at this equation, it kind of looks like we have most of what we need here. Let's say our Fc is going to be 100 newtons. We have a mass of 20 kilograms. We don't know the speed, it's actually what we're looking for. And we have an r of 1 meter. Now, just by this, we can solve the question of how fast can it spin until it breaks. The question is asking, what is the maximum speed it can spin before the pendulum breaks due to tension? So we have our maximum tension, we have our radius, we have our mass. Let's solve for velocity. So we have 100 divided by 20 equals speed squared. So 5, or root 5 equals v, absolute value, equals speed, and root 5 is about equal to 2.236, which means max speed is 2.236 meters per second. And that is our answer for that particular problem. Great. Let's move on to another problem. Let's say we have a track here that's 10 meters in diameter, and there's a dude running along this track at a constant speed of 5 meters per second. And this guy weighs 30 kilograms. So let's list what we know here. We know our speed is going to be 5 meters per second. We have a mass is 30 kilograms. And we have a radius. It's 5 meters. Be careful, not 10 meters. 10 meters is the diameter. Now, the question I'm asking is, find centripetal force value. Well, the centripetal force is equal to m speed squared over r, and we have all those, so we can just plug in our numbers. Of 30, do 5 squared, and then a radius of 5, and that gives us 150 newtons as our centripetal force value. Now, let's do one more example, and this one's a little bit more complex. In this problem, we have a roller coaster with a loop-de-loop. Imagine this as a loop-de-loop on a roller coaster. And on this loop-de-loop, the roller coaster car has a constant velocity, constant speed of 20 meters per second. So at the top, the car goes this way at 20 meters per second, and at the bottom, the car is still going at 20 meters per second. We know the diameter of this loop-de-loop as 40 meters, and we know the mass of the roller coaster car is 1,200 kilograms. And the question is, at the top and bottom of the loop, find the normal force. Now, normal force, we haven't really discussed normal force today. What on earth does this have to do with uniform circular motion? Well, a lot. Let's take a look at the top of the loop-de-loop first. So at the top, we have our roller coaster car. And the track is going to be above the car here. So we have a normal force pointing down. And any other force we can think of? I sure can. There's gravity. So we have two forces pointing down. And since this is the direct top of the car, pointing down means it's pointing at the center of this circle, which means that is the centripetal force as well. But it's not just one force here. The centripetal force is Fg plus Fn. Both of these forces are center-seeking here, so both of those forces contribute to the centripetal force. So let's look at the centripetal force equation. Fc equals m speed squared over r. We actually know everything we need for finding centripetal force. We have a mass, 1,200 kilograms. Our speed is constant, so 20 meters per second squared. Our radius is 20 meters, which is because our diameter is 40 meters, so our radius has to be half that, which is 20. And we can find our centripetal force to be 24,000 newtons. But that's not what we were asked. We were asked to find the normal force value. So what can we do here? Well, we know that Fc is equal to Fg plus Fn. If we were to isolate Fn, we could say Fn is equal to Fc minus Fg. And hey, we know Fc. So we can plug in 24,000 newtons into Fc. So do we know Fg? Well, we do. As you probably know, Fg is equal to m times g, g being the gravitational constant. So we can say that Fg is equal to mass times g, which is 1,200 kilograms, that's the mass, times the gravitational constant, 9.81, and now we have everything we need to find Fn. And if you were to take out your handy-dandy calculator, you can easily find that Fn is 12,208 newtons at the top of the loop-de-loop. So that's only half the problem. We do have to still worry about the bottom. So let's do that. At the bottom, let's draw another FBD really quick. Just like the last one, we have FG, but this time our FN is pointing upwards. Because remember, at the bottom of the track is underneath the roller coaster car. So normal force has to be pointing upward. So what now? Well, FC here is going to be a little bit different. And that is because FG is no longer pointing towards the center. It's actually pointing directly opposite. It's pointing away from the center. But that still means it's part of the FC equation, because anything that is center seeking or the opposite of center seeking needs to be taken into consideration. So instead of FG plus FN, our equation here has to be FC equals FN minus FG, because FG is pointing the opposite direction of the center. We can see this in this diagram. If the center is right about here, and we're trying to find centripetal force, the centripetal force is Fn going towards the center. Great, lovely. But Fg going the exact opposite, which means the magnitude of the centripetal force is going to be different since we're subtracting Fg instead of adding it. Let's take a look at this problem and try and find the normal force. We can find the centripetal force pretty much the exact same way. M speed squared over r. And we can plug in 1200, 20 squared because it's still 20 meters per second at the bottom, and 20 meters. And that looks familiar. It's actually exactly the same as the centripetal force at the top. It's 24,000 newtons. That didn't change. But now our equation for Fn is going to change. If we isolate Fn, it's going to be equal to Fc plus Fg. And Fn is equal to 24,000, which is Fc, and then Fg. Do we know Fg? We do know Fg. It's exactly the same as what it was before. Mg is going to be 1200, which is m, times g, 9.81, and beautiful, we now can find Fn. If you take out your handy-dandy calculator, you can find out that Fn is equal to 35,772 newtons for the bottom of the loop. Well, that's all for my discussion on uniform circular motion. I hope you enjoyed and I hope you learned something today. If you enjoyed the video, go ahead and like and subscribe and do whatever else people on YouTube do, and it would mean a lot to me. I'll see you in the next tutorial. Happy learning.